Today we're going to be talking about friction and some of the more confusing points about friction. So friction, as you'll remember from last year, maybe we taught you that friction is a force that opposes motion. And I'm not sure that that's the best definition for friction, but what friction really does is it's a force that opposes the relative motion between two surfaces. And we'll talk more about the details of that in this video. Last year we told you that there are two types of friction between solid surfaces, and that's what we're focusing on as well here. There's kinetic friction, where the two surfaces are moving relative to each other, and there's also static friction. In static friction, that means that the two surfaces are not moving relative to each other, but the surfaces themselves could be moving relative to some other point as well. It's worth a mention that static friction is a variable force, meaning that it can range in magnitude between 0 and some maximum value. So kinetic friction is a little bit easier to pin down than static frictions in a lot of problems. And we'll talk more about that in this video. So today we're going to be focusing really on weird examples for friction. If you want more basic examples, you can go to YouTube and you can search friction Khan Academy. And the Khan Academy has some nice basic physics videos, but the physics that we're actually going to be studying this year is a little bit more complex than is covered in this Khan Academy. So you can go there for the basics, but I'm going to be telling you some of the more intricate features of some of the topics we'll be studying. So that's that. Okay, let's get started with kind of a weird example. Let's say that we have a tire that is on a road, and usually tires are attached to cars or bikes or something else that's moving. So you would think that this tire, since it's attached to a moving thing, would experience kinetic friction with the road. But that's actually not the case most of the time. Usually we are dealing with static friction, because this point on the tire is not moving relative to the surface. In fact, there's rolling happening in the normal circumstance, so these two are not moving with respect to each other. If this tire were skidding, then we would have more of a kinetic friction situation. But most of the time when we're looking at a tire, we're looking at a static friction situation. That's not to say that there isn't any friction when we have tires. If you remember last year in honors, we used the quote-unquote friction-free carts. They're not really friction-free, but they are designed to reduce friction. But there was some friction, and of course you want this friction between the tire and a road to be a high coefficient of friction, because you don't want it to slip into kinetic friction. But where we do encounter some friction in the system is at the axle. So there will be some kind of rubbing, kinetic friction involved here at the axle. So that's just kind of a weird example of some friction. Okay, let's consider another example where we have a car that's going in uniform circular motion. Maybe it's a car that's doing donuts in a parking lot. So here's my car, and we're looking kind of at a bird's eye view as if we were in a helicopter or something, and we want to talk about what's keeping this car moving in a circle. Of course, since it's in uniform circular motion, there must be some centripetal force pointing in towards the center of the circle. That's what we know. But how do we figure out what exactly that is? Well, one technique I use a lot to think about friction is to imagine the situation if there were no friction. In other words, if this were all ice and there were no friction, what would happen to this car? Well, most of us know by this point that the car would actually fly off tangent to the circle because the tires wouldn't be able to grip the road. So it would go in a straight line by Newton's first law and go off from the circle. So what's keeping it into the circle? Well, what's keeping it into the circle is the force of static friction, which will be in towards the center of the circle. Okay, so this car is going this way around the circle. Okay, so if we had to draw a free body diagram, let's actually take a different view and look at the back of the car. So these are the tail lights. I'm not going to draw the tires in, but I'm going to use this box to represent the car. And we're going to think to ourselves, okay, you know, are there any field forces? Yes, of course. There's a field force pointing down, the force of gravity. And are there any contact forces? In other words, is this car touching anything? And yes, the car is in fact touching the ground. So when we have contact with the surface, we have the capability of two forces arising from that. The first one of those is the normal force, which acts perpendicular to the surface. The second is going to come into play, is the force of friction. And in this case, friction is going to point in towards the center of the circle because the friction is actually going to keep it moving to the right. So see how on this track the car actually moves to the right, so friction must be acting to the right at this point in time. Now if we were just to finish out this free body diagram, we're going to know that since it's moving in uniform circular motion, that the acceleration of this object is in towards the center of the circle, so I'm going to indicate that, and then I'm going to pick an appropriate sign convention, which means that acceleration is in the positive direction, and I'm going to circle that and stick to that sign convention throughout the duration of the problem. Okay, so that's kind of another funny example. Okay, let's consider a more complex example of two blocks. One is sitting on top of the other, and it's on tabletop. This tabletop is frictionless. I should say the interaction between the bottom block and the top and the table is frictionless. And this bottom block is going to be pulled by a string. I'm going to just label that the force of tension. And this thing, what's going to happen in this scenario that I'm giving you is these two blocks are going to move together. So there must be friction between the bottom and the top block that makes them stick together. Okay, so first I'm going to look at the situation from the standpoint of the system. So I'm going to draw a free body diagram for the system. Because it's actually moving together, everything's moving together, we can actually draw this free body diagram of the system. So are there any field forces on this system? And the answer to that is yes. There's the force of gravity of the system. Are there any contact forces? Now that means what is this system touching? Well, it's touching the table. So from that, there can be two forces generated. The first one is the normal force. And the second one would be friction. But remember that this tabletop is frictionless, so we're not going to include a force of friction here. This is on the system, so even though there's internal friction between the two blocks, we're not going to consider that. This is a free body diagram of the system, all the external forces. Okay, finally there's the string that's attached. We're going to draw in the force of tension. Now what we can tell from this free body diagram is that the system is actually has a net force to the right, so the acceleration must be to the right. So that's the acceleration of the system. And since the blocks are stuck together, that means that the bottom block also experiences this acceleration and the top block also experiences this acceleration. So each of the two individual blocks accelerate the same way that the whole system does. So now let's start to investigate this internal force of friction. And we're going to do that by first looking at the top block. Okay, are there any field forces on the top block? Yes. there is the force of gravity pointing straight down. And I'm just going to call that FGT for top block. Okay. Is this block touching anything? Yes, it's touching the bottom block. Okay, so which way is the bottom block pushing on the top block? It's pushing up. Now this is like a normal force, or I'm going to just call it F sub C for the contact force between the two blocks, but it's really a normal force. And when we have a force of contact between the surface, there are two forces that can arise, the normal force, which is here, and the frictional force. Now we got to figure out which way the frictional force is going. So one way to do that is to consider that we know that this block is accelerating to the right, so we must have a rightward acceleration and a rightward net force. So one way to think about it is there's only one force left that we haven't drawn, and that is the force of static friction. So it must go to the right. Okay, so that's one way of thinking about it. Another way of thinking about it is, what would happen if there weren't friction here? Well, what would happen if it weren't friction here would be that this bottom block would be pulled out from underneath this top block, and the top block, because it has inertia, would just stay in its place. It wouldn't move until the bottom block was pulled completely out from underneath it, at which point this top block would fall. So what friction does is it opposes that motion that would happen if there weren't any friction. So if there weren't any friction, it would stay still, but with friction it moves to the right, so the frictional force must be to the right then. So those are two different approaches. Now let's investigate the bottom block. Are there any field forces on the bottom block? Yes. The force of gravity for the bottom. Are there any contact forces? Well, the obvious one is that there's force of tension here. Okay. It's also touching the bottom. So we're going to draw in here the normal force, Fn. I'll call that Fnb, although I know it's the same as the Fn of the system, but we'll leave that there for now. There's no friction generated down here. And then what else is this bottom block touching? It's touching the top block. And which way is the top block pushing on the bottom block? Well, it's pushing down with a force Fc. This is the force of contact. These two forces here and here are equal and opposite forces by Newton's third law. But there's one other Newton's third law force, and that is the force of static friction. One way to determine the direction of the force of friction on this bottom block is to look at this top block and see that since it's going to be a Newton's third law force, they have to be in opposite directions. So this force of static friction must be to the left, because these two must be equal and opposite. The other way to think about it is what happens when there's no friction between these two blocks. Well, as we said, that this bottom block would be pulled out from underneath the top block. And so it actually would be easier for the person pulling if there were no friction. Imagine that this top block is very, very massive. If we're just pulling out the bottom block from underneath it, it's not going to be nearly as hard as if I have to pull all of this mass with all of this inertia. So the force of static friction, the fact that the block is going to stay attached, must actually hinder the motion that the person who's pulling is providing. So that also indicates to us that this static frictional force should be to the left. Just to finish out these free body diagrams, we could give ourselves a sign convention to use with all three, and it's good to stay consistent throughout the problem. One other thing to note is that you see this static frictional force. This is kind of funny in a way because this block is actually moving, so it's kind of weird that it's a static frictional force, but again, we're talking about the relative motion between these two blocks and these two surfaces, and these two surfaces aren't moving relative to each other. The other thing to note is that we said, you know, maybe last year you learned that friction opposes the motion. Well, this is actually helping the motion. So we don't want to stick with that definition there. Okay, I have one more example for you, and that is on an inclined plane. So let's say that I have a very heavy object on an inclined plane, say it's a refrigerator on an inclined plane, and there's friction here between the inclined plane and the refrigerator. So it's just sitting there now, it's at rest, and we can draw a free body diagram for that. So that's the force of gravity of the refrigerator. It's touching the inclined plane, so here's the normal force, and we got to consider the force of friction, static friction, that happens between the block and the ramp here. And we can do that by, again, using that technique of what would happen if there were no friction. And the answer to that would be that this refrigerator would slide down the ramp. So friction must be holding it on the ramp, so friction must be pulling it up, and that's the force of static friction. The difficulty comes in when we actually get on the ramp and start to try to pull the block up the ramp. So I'm actually going to be trying to pull this up the ramp. And the tricky part comes in talking about which way the static frictional force goes. So in this new situation, I'm going to draw a new free body diagram. Here's my force of gravity, my normal force. And now let's just say that I just started to pull just a little bit. I'll call that the force of tension. You could call it the force applied if you'd like. If we just start to pull it a little bit, then what happens is, like, let's say it's going from slack to no slack. The static frictional force is actually helping you in that, you know, the refrigerator is not going to fall down. It's not going to slide down the ramp. So in this case, the static frictional force is still upward. You'll get to a point as you pull harder and harder, though, that you actually could be pulling hard enough that you don't need the static frictional force, in which case this force of tension would end up equaling this static frictional force here. So in this case, we're in static equilibrium. Our sum of the forces is equal to 0 in all directions, and we don't need the static frictional force. Remember that static frictional force can be a 0 force. So this is just a perfect situation where I'm pulling just at the right amount of tension that we're not moving, but we don't need that friction. But then when you start to pull just a little bit harder than that, then we run into a situation where we're starting to try to get it to move, but it's not moving yet. So in this case, the force of static friction will oppose what you're trying to do. It's going to kind of hurt you from moving. So these are three different situations, and it kind of depends on the numbers at this point. How would you figure out which way the static frictional force points? Okay, one way to approach it is to look at this situation and figure out exactly how much tension you would need so that this thing didn't move without friction. And if you have a lesser tension than that, then the static frictional force is helping you. If you have a greater tension than that, then the static frictional force is hurting you. But so that's one way to go about it. You have to do a little bit of legwork to just figure out the numbers, to figure out which way the static frictional force points. And then, you know, you got to figure out whether static friction can actually hold the block on the ramp, or how much more can you pull to overcome the static frictional force, at which point you're going to turn this force into kinetic friction once we've overcome the static friction. So there are a lot of considerations in this sort of problem, and just to finish out my free body diagrams, I'm just going to pick a sign convention that I'll stick with for the rest of the problem. But yeah, so this is one of those weird cases where you do need to figure out you know, which direction the static frictional force goes just by really thinking about the problem and maybe doing some preliminary calculations. All right, I hope that helped clarify some of the weirdisms that happen with friction, but I think the bottom line is that you can use a couple different techniques, which are to think about what happens when there's no friction, think about you know, what your acceleration should be in this kind of situation and which way the static frictional force will point in that situation, and also do a lot more thinking and some legwork on a problem of this complexity. So make sure you write down all your questions about this video and bring them to class so that you can get them answered. See you there.